All right. Well, this mini lecture will begin to cover the chapter in your book that is called The Family of Stars. I prefer to call this section Observational Properties of Stars because it's all about the properties of stars that we can discover just by observing them with telescopes, spectrometers, and by being clever by using the basic laws of physics and properties of light. So there's generally 5 basic properties of stars that we can measure by observing them here on Earth. The first one is surface temperature. We can figure out the surface temperature of a star. We know that we can get a rough idea of the surface temperature of the star just by looking at its color in the sky. A blue star, for example, is hotter than a white star. A white star is hotter than a red star. And we learned that in the chapters on spectroscopy. Composition. By composition, what I mean is the elements or chemicals that a star is made out of. We can also use spectroscopy for that. We know that a star generally will show an absorption type of spectrum. We talked about that in the chapter on spectroscopy. And by looking at those spectral lines, and again, being very clever because it's not always a straightforward thing, we can determine how much of each chemical element comprises the star. So what we're going to find is that stars are primarily made of hydrogen and helium with only trace amounts of other elements. The star's luminosity. Luminosity is just a fancy word for how bright the star actually is. The star's intrinsic brightness. What I mean by that is it's not related to, well, it is related, but it's not how bright a star looks necessarily, but how bright the star actually is. When we look up into the sky, we see bright stars, we see dim stars, many stars. They're so dim that we can't see them with our unaided eye. But that's a property of both the actual brightness or intrinsic brightness of the star and its distance. Just like light bulbs, if you have a dim light bulb that's right next to your face, it's going to look brighter than a bright light bulb that's at the other end of a football field, let's say. So luminosity is really a measure of how bright the light bulb is, rather than how bright the light bulb looks to you. And it's a very, very difficult thing to figure out luminosity. We'll get to that in a few minutes. The size of a star. Now, by size, I don't mean the mass. I mean the physical amount of space a star takes up. For example, its diameter. Most stars are spherical, and because of that, you can measure the girth of the star, its diameter. Or you can measure the volume that the star takes up. For example, our sun is about 100 times the diameter of the Earth. So if you measured from side to side the diameter of the sun, you could fit 100 Earths from side to side. However, if you had a hollow sun and you wanted to fill its volume with Earths, you would have to have 100 times 100 times 100. You'd have to have over a million Earths, basically, to fill up the sun with little Earths. So we're going to talk a little bit about the size, how you figure out the size of a star. The interesting thing is, it turns out that we can figure out the size of the star without actually measuring it directly. Because if we know the surface temperature, okay, and we know the luminosity, those two things are related to each other by the size of the star. Okay. So if we know surface temperature and we know luminosity, we can eventually find size. Okay. And we'll see that in just a little while. And then the 5th property of the star, which is probably the most difficult to measure, and we can't do it for every star, but is absolutely essential for understanding stars. It's probably the most important property of the star, is its mass. And again, by mass, I do not mean size. I do not mean how big it is. I mean how much stuff, how many kilograms of matter are in the star. Okay, so let's go right along and start talking about temperature. By temperature of a star, what I'm really talking about is its surface temperature. Okay, I'm not talking about the internal temperature. I'm not talking about the temperature of the star's core, where we're going to find out is where all the action is really. What I'm talking about is the temperature of its visible surface. And there's three ways to estimate the temperature of the star. Now, first way we talked about that you learned in the chapter on spectroscopy is that stars radiate as though they are, at least the underlying continuous spectrum of a star radiates as though it's a solid hot object, like a hot poker or a hot frying pan that's glowing or something like that. Now, by the color that the star gives off, you can estimate its temperature. Okay, so we talked a little bit about Wien's law. This is an actual equation that where you can figure out the peak wavelength. Okay, for example, this is what we call the peak wavelength, the summit, if you will, of a hill of the intensity diagram. Okay, the peak wavelength is basically inversely proportional to the temperature. Okay, if you have a relatively low temperature, like 3,000 degrees Kelvin, you have a fairly long peak wavelength, somewhere around 1,000 nanometers. Okay, if you double the temperature to 6,000 degrees, the peak wavelength gets cut in half to somewhere around 500 nanometers. And then if you double it again to about 12,000 degrees, the peak wavelength gets cut in half yet again. Okay. Here, somewhere around 250 nanometers. Okay. Now I'm just approximating those numbers. And in fact, Wien's law is a little more precise than that. In the previous Astronomy 121 course, we usually use 3 million over the peak wavelength to kind of throw away that second digit or round up to only one digit. The more precise version of the law is 2.9 million divided by the peak wavelength gives you the temperature. Okay. So if we could take the spectrum, the underlying continuous spectrum of the star, and figure out where the brightest part of the spectrum is, in other words, the peak wavelength, okay, we could figure out what the temperature is, okay, within pretty good accuracy. Now, that's a tedious and difficult and long process because there are so many stars in the sky. So that's not always something you want to be doing. Okay. A variation, a quicker and maybe slightly less precise way of doing this is to measure a star's color. Okay. Because the peak wavelength is determining the star's color, you can figure out roughly how hot the star is on its surface by measuring its brightness in 2 or 3 different colors. Okay. So for example, let's take a look at this one. This star is a 3,000 degree star. So basically, if you measured how bright it was in the red part of the spectrum, you would see that it would be brighter than it is in the green part of the spectrum, what we would call the middle of the visible portion of the spectrum. And then it would be very, very dim here, almost non-existent, in the blue part of the spectrum. So this star looks red. It would be what we would call a red-hot star. Okay. If we had another star with a higher temperature, okay, this one, for example, which is at 5,800 degrees, which is almost like exactly the temperature of our sun, we could round it up to 6,000 if you wish. But you'll see that the brightness here, the height of this graph in the red, this much here, is a little bit less, but not much less than it is in the visible here. Okay. And it's about the same as it would be in the blue and violet, which is what we have right here. Okay. So this star looks, well, this graph says it looks yellow-white. I think it looks white. Okay. This is a white-hot star because the colors across the spectrum are more or less even. And because they're more or less even, you don't get much difference at all, and your eye perceives that not as red or blue, it perceives that as white. Finally, if we crank up the temperature of the star even more, in other words, we go to look at an even brighter star, say one that's at 10,000 degrees, the star that's at 10,000 degrees, by the way, actually gives off most of its light in the invisible ultraviolet part of the spectrum. Okay. Now, most of that light does not make it through our ozone layer, and that's actually good news for us. But let's just see about the visible light that we can detect. The brightness of the red and orange part of the spectrum would be lower than the brightness of the yellow and green part of the spectrum, right here. And then the brightest part of the spectrum would be between the violet and the blue, right here. So as far as the colors that we can see with our eyes go, the blue color would be brighter than the visual or greenish yellow color, which would be brighter than the red or orange color. And in fact, astronomers use filters when they try to use this technique. They will use what's called a B filter to let through just the blue and violet light. They will use a V filter to let through mostly the green and yellow light. And they will use a B filter to let through mostly the orange and red light. And so that by doing this, they know that if the star is brighter in the blue filter than the visible or the red, sorry, I used B instead of R for red. Get rid of that. So this is the R filter right there. Then they know it's a hot star. And in fact, if they know the exact ratios, they can figure out that it's about 10,000 degrees. On the other hand, if you have a star where you have approximately even brightnesses, like this one here, you have approximately even brightnesses across the spectrum in the B and the D and the R, you're going to have a star that's around 6,000 degrees. And then if you have a star that's brightest in the red compared to the visible and the blue, then you know it's a fairly cool star, like 3,000 degrees. Okay? And so this technique is called photoelectric photometry. It's basically measuring a star's brightness using these standard filters. Here's just a drawing of some of the band passes, as they call them, of these typical filters. Basically, where this curve is high, that's where the filter transmits a lot of light, and where it's low, that means that's where it blocks out most of the light. Okay, so U is for ultraviolet, the near ultraviolet. D is for blue, that would be like violet and blue mostly, and a little bit of green perhaps. And then visual would be mostly green and yellow, and maybe a little bit of orange. And then there would actually be another one here called the B filter. Okay, I'm sorry, the R filter. Well, I feel like I have trouble with R today. The R filter would be here. That would be the red filter. And there's even an infrared filter out here called the I filter. Okay. The reason that's important is because if you have a bunch of stars in a cluster, you don't have time to take a spectrum of each one of them. And so using this UBV spectrometry or photometry would actually be a much faster and easier way to try to figure out the temperature of a whole bunch of stars all at the same time. Okay. So that finishes this mini lecture. We will continue with part 2 coming up.